Hi, I'm Dr. Kyle Montgomery, and in this video we're going to be looking at RLC circuits, and a little bit different from some of my other videos. Here I want to just kind of go through sort of the general process by which we are able to determine what, in general terms, what the responses are for a given voltage or current in a variety of different RLC circuits, okay? So I'd encourage you to maybe pause the video, copy down what I have here. So we're going to look at two specific cases. If we have a parallel combination of resistor, inductor, and capacitor, and a series combination of the inductor, resistor, and capacitor. And both of these, you can see that I have no source. So what we're talking about here initially is known as natural response. Okay, where natural response is basically indicating that the circuit might initially have some, let's say, charge, some voltage built up on my capacitor, or might have some current built up in my inductor on either one of these two cases. But as you can see, I've disconnected whatever my source was. Maybe I had to switch to some other current or voltage source over here. And therefore, the currents and voltages are all going to eventually just decay down to zero once it reaches the steady state condition. And so what we want to do is basically evaluate, how do we go through this process of determining what the final solutions for, let's say, a voltage or a current might be in either one of these circuits based on the various elements that we have there. Okay, so we'll just take a quick pause and allow you to do that, and then we'll get right into it. Okay, so what we're going to do here is basically look at each one of these two circuit cases, the parallel case and the series case, and I kind of want to go through them in tandem. Sometimes we separate these and maybe only just look at the parallel and then go back and look at the series case. Here I'm going to kind of try to do them together so we sort of see that there's a lot of commonalities between the approach that we do for both the parallel and the series case, and it ultimately gets us to seeing how the solution is very similar to each of these. There's only just some relatively minor differences, okay? So if we look at initially the parallel circuit case here, and we say initially just want to write, we need some relationship, some equation that's going to describe the voltages and the currents happening in this parallel combination of the capacitor, inductor, and resistor. So if we think about just writing a KCL equation, maybe from the top node, and indicate each current here going down through each branch, IC, IL, and IR, okay? So we know that all of those would have to sum to zero by Kirchhoff's current law. So instead of, or let's just start here by saying what we know, IC plus IL plus IR all have to equal to zero, okay? So now then, how can I describe these currents in terms of some other known quantities that I have? So if I say in total, let me indicate just the voltage in general terms by lowercase v across each of these different branches. So I know that the current IC I could use by just saying C dV dt, because we know that C times the derivative of the voltage describes the current through a capacitor. So that's what IC is. For IL here, this would involve the integration, or 1 over the inductance times the integration from 0 to t times the voltage times d tau. That's the general term for any time t, and then because we might have some initial current here, we're going to add in plus I naught. So that's just my initial current condition. And again, these two terms are just in general for any inductor, telling us what the current through that inductor should be as a function of time. And then finally, for the current through my resistor, IR, well, here I could just use Ohm's law to say that this is V over R. And so again, all those terms should still sum to zero, okay? So here we have still a little bit of a tricky equation that we're having to work with. So let's do a couple of things to get it to a form that is a little bit more easy to approach. So the first thing I'll do is take the derivative of this equation with respect to time, which I can do that on both sides and not change anything about the problem here. So if I take the derivative of my first term here, then I'll turn this into the second derivative. dv on top over dt squared here. And for my next term, so this will, by taking the derivative of this integral, basically just leaves me with V over L. I naught is a constant. If we're taking the derivative of a constant, that just goes to 0 there. And then for my final term, which is V over R, taking the derivative with respect to time, we would have 1 over R times dV dt equal to 0 there, okay? So we see now already that we can tell that we have a second order differential equation because I have a secondary differential here, first order here, and then just our primary term in the middle. We'll rearrange this. Let's divide by c so we can get the second derivative by itself. So then I'm left with d squared v over dt squared. If I've divided by the capacitance c, so I have 1 over, or let me bring 1 over RC times the first derivative, the voltage, and then 1 over LC times V equals 0, okay? So here then is our final second order differential equation that we have that's describing, in this case we're looking at the voltage as a function of time in this parallel RLC circuit, specifically of the case of natural response where we have no other sources that are tied into this circuit. So that's why everything here is just equal to 0. And it gets us in a nice form that we can look at and then kind of try to evaluate, well, what should the solution to this second order differential equation look like? And then what are some characteristics of it from there? So taking note of this, I'm going to go ahead and erase this, and we're going to go through the same process now for the series circuit. Again, I just kind of want to a little more clearly illustrate how there's a lot of parallels between what's going on in the parallel case and the series case. It's still going to get us to a second order differential, as you might expect. So we'll go ahead and do that now and then go on to the next steps of how to actually find a solution to these equations, okay? Okay, so now let's go through the same process for writing some relationship around this series circuit that I have here. So here, instead of applying Kirchhoff's current law, it'd make more sense to apply Kirchhoff's voltage law, meaning I need to add up all the voltage drops around this loop here. Again, we have no other sources, so I know that the sum of these voltages just must be equal to 0. If I indicate, in general, just some current, lowercase I, as such, then initially if I start off with the voltage drop across my resistor R here, I know that that should just be I times R by Ohm's law. The voltage drop across my inductor would be L di dt. Again, that's just standard form for what we know about inductors. And then the voltage drop across my capacitor would be plus here 1 over c, so we have the another integral that we're looking at here from 0 to t, the integration of the current, the integration term d tau, plus the voltage V naught here, okay? And maybe just to be a little bit more accurate, let me indicate this voltage as being plus to minus here, so that way we're in the right terms here is what we have. And then so that's the 3 voltage drops I have around this series loop. All of those should equal to 0 by Kirchhoff's voltage law. So now then, just basically applying kind of the same process we did when we were looking at the parallel circuit case. The first thing I'm going to do is take the derivative of the current with respect to time. That'll allow us to kind of eliminate having an integral mixed in with what we have right here. Okay, so if I have this, then I need R di dt. Okay, taking the derivative of this IR term plus L. This would take me to the second derivative of the current times my inductance L. Okay. And then here I would just be left with I over C by taking the derivative of this integral. And of course, again, V naught here is a constant. So taking the derivative of that just gives me 0, so that doesn't factor into the equation any longer here. Equals 0. So now again, we already see we have our second order differential equation. I'm going to do a little bit of cleanup. Again, I want to kind of isolate the second derivative term. So in this case, I'm going to divide by the inductance L, and then just kind of rearrange the terms that we have here. Okay, that's my second derivative term, first derivative term here. So now I have R over L times di dt, and plus 1 over LC times the current I equal to 0 here, okay? So again, now what we have here is the second order differential equation. As you can see, a very similar form to what we saw in the parallel circuit case. Now one, of course, big difference is that in this case we're working with the current specifically, whereas with the parallel circuit case we're working with the voltages. But in any of these cases we will actually end up seeing that the response of the voltage and the current in any given RLC circuit is basically going to follow the same characteristic more or less. So it doesn't matter whether we're evaluating things in terms of the voltage or in terms of the current, the response, the solution that we're going to get to, the form of it will take the same. The only differences will be looking at initial conditions and final conditions and how those obviously would be different for a current versus a voltage. But here again we just have a very similar form to the parallel circuit case, as you can compare in your notes there. And so now we can look at how do we use this second order differential equation to actually find, how do we find a solution to this second order differential equation, okay? So the basic process that we're going to follow is to basically start with some assumption about what the form of the solution should look like. And in this case, we're going to make the assumption that the form of the solution is going to have some exponential term just with some coefficient. So here we're talking about the voltage as a function of time is going to be just some coefficient a times exponential to a term s times t, which will kind of go into finding what this term s is. So this would be for the parallel circuit case because it's a voltage specifically. But I could say the same thing about the form of the solution for the series case, where here we're looking at the currents, where I could say that the current is going to take some form of coefficient with some exponential as given here, okay? Okay, so now the basic step here is if we were to then take this form of the solution and plug it back into the differential equation, which again that is what we would normally do if we're assuming that this is the solution, well that means this solution should in fact complete this equation such that it should actually equal out to 0. So if we were to do this, plug this back into the second order differential equation, do a little bit of reduction in terms, I'm going to kind of skip over some of the steps, but we'll see then how we get to what's called the characteristic equation, which is going to be an important term that tells us something about this term s here. So let me go ahead and clean up my board here and then we'll get into looking at that specifically. Okay, so again, if we took the form of the solution that we had previously, plug it into that second order differential equation, we can factor out the exponential from that, and what we're left with is basically what's called the characteristic equation, which takes the form as follows. It looks like s squared plus s over r times c plus 1 over L times c equals 0. Now this is specific for the parallel case. Okay, because again, this is just taking into account that we came up with two separate second order differential equations, one for the parallel, one for the series, and they more or less had the same form, but there were some different terms that we saw in there. So again, this would be specific for the parallel case, and then what we'd have for the series case, very similar, but specifically still s squared plus r over L times s plus 1 over LC equals 0, okay? So these are what are known as the characteristic equations for each of the parallel and the series RLC circuit case. And then in order to be able to find, basically, again here S is the variable that we would need to sort of solve for this equation to be valid. And so if we look at what those should look like for both the series and parallel case, right, just basically applying the quadratic form here. So we should have two roots of each of these equations. Again, they're going to be slightly different for the parallel and series case, but still very similar. For the parallel case, it will come out to be minus r over 2L, and then plus or minus the root of r over 2L squared minus 1 over L times C. And then for actually, sorry, I think I indicated that wrong. This should be actually the series, the roots of the series characteristic equation. And then the one for the parallel would give me, the roots are going to be equal to minus 1 over 2 RC plus or minus the square root of 1 over 2 RC squared minus 1 over LC. Okay. So again, the only difference here that we see between these, the form of the roots for the series versus parallel case is basically a couple of the coefficient terms here and here specifically are a little bit different. We still have the 1 over LC, which is the same. Again, that kind of makes sense by just looking to what we have from each of the characteristic equations up top. Okay, but again, still basically a very similar pathway for both the parallel and series solutions. Okay. So now if these are the roots that we found, S1 and S2, if we think back to the solution that we've assumed, okay, which again took the form of, say, voltage as a function of time was equal to A times the exponential to the S to the power of S times T time. Okay, so here we're saying these roots, S1 and 2, where it's S1 and 2 simply indicating that I can either add or subtract this quadratic term. But either one of those should be able to plug into the form of the solution and give me, in fact, a valid solution. So as we know from what math tells us with differential equations, if either one of these roots is a solution, then we also know that the sum of each of these forms of the solution would also be basically a third solution. So that's the form that we're going to work with to actually come to a more generic solution for the RLC circuit case. So let me kind of erase what I have here, go on to looking at what those forms of the solution actually do look like. Okay, so again, what I just described in words was to say that because we are able to distinguish two different roots, this S1 and S2, that tells us that I can have two different forms of the solution, but we also know just from what math would tell us that an additional solution would be the sum of those two solutions. And so this is the form we're going to work with, where we're basically encompassing both S1 and S2 and just differentiating that these coefficients A1 and A2 are going to be distinct in generally speaking, okay? But now the actual form of the response then we can actually break down to being three different forms based on the fact that in taking the roots of the characteristic equation, these roots S1 and S2 themselves might have a slightly different form themselves. So there's going to be three different cases that we're going to examine that we could possibly encounter. So in one case, again, talking about the roots S1 and S2, they could both be real and distinct. And this would be what we call the overdamped response. Okay. The second option is that both of the roots are actually complex and still distinct. Well, they're distinct, but specifically they'll actually be conjugates of one another. Thinking about to our complex math. And this will indicate as being a so-called underdamped response. And then the third and final option that we could have is to say that both S1 and S2 are actually, they're real values, but they're also equal. Okay, and this will be indicated as the so-called critically damped response. Okay. So again, this is just indicating that because we're dealing with the characteristic equation, we're taking the roots of that characteristic equation. Those roots themselves could be either real or complex. And so based on what the conditions are, that will fall into one of these three categories and tell us about the type of response, overdamped, underdamped, and critically damped, that we might possibly have. So now let's get into kind of how do we evaluate, if we're looking at any given circuit, how will we know which one of these specific damping responses would we be in without having to necessarily always solve for S1 and S2 specifically. They're actually a little bit of a shortcut. We can look at to determine which one of these categories we kind of fall into. Okay, so now for finding out which of those three different types of responses that we have, what we can do is compare two frequencies. We're going to define omega naught and alpha. So omega naught is known as the resonant radian frequency. Okay, and then alpha here is the so-called Neper frequency. So each of these two frequencies actually come into play when we're talking about the roots, because the roots, well, basically what we're doing is making some substitution here in the roots of the characteristic equation. So S1 and 2, we could basically make these substitutions as minus alpha plus or minus the square root of alpha squared minus omega naught squared. So then you can see, if you compare again in your notes back to what we found for these roots, we're basically just plugging in the values that we had in those coefficients for what we have now as alpha and omega naught. So specifically in the parallel circuit case, that means that alpha is just 1 over 2 times RC, and omega naught is equal to 1 over the root of LC. And then for the series case, we come up with alpha being slightly different here of R over 2L, but omega naught is actually the same quantity here, 1 over root LC. So this is only just one minor difference. And so what we'll see then is if we compare omega naught to alpha, whether or not one's bigger than the other or whether or not they're equal, that's going to tell us which of the three types of damping responses we will actually have, and then which form of the solution that we can use to evaluate what we have. And again, see here that there is still very much a lot of similarities between the parallel circuit case and the series circuit case. The only difference that we really see is between the two forms that alpha takes, is where you kind of have to draw your distinction as to understand, are you looking at a series RLC circuit or are you looking at a parallel RLC circuit, and then you would need to apply one of these two forms of these frequencies to come up with a value. Now just one other note about these two frequencies in terms of the units. The units are, because these are both angular frequencies, they're in terms of radians per second rather than just hertz or inverse seconds. Okay, so let me erase this, then we'll kind of go through just evaluating based on these two frequencies, how they correlate. Will tell us the type of damping response, then let's look at the form of the solution that each of these takes. All right, so to know again which of these three types of responses that we fall into, we're just going to take a comparison between those two frequencies that we just defined. So for the overdamped case, this would be if omega naught squared is less than alpha squared, then we would know that we have an overdamped response case. For the underdamped response, that would just be the exact opposite. Omega naught squared is greater than alpha squared. And for the critically damped response, this would come into play if these two frequencies are exactly equivalent. Okay. So now, if we've defined which type of response that we had a general form of the solution, but what we actually find is because the roots in each of these cases were a little bit different. Remember the overdamped response, we're talking about we're having real and distinct roots. The underdamped, we're dealing with complex quantities, and critically damped, still real, but they're equal. That kind of comes into play then for the general form of the solution that we have to work with in each case. And what it works out to be is as follows. So if we're talking about in the overdamped case, here we're basically left with what we already saw previously, where let's say the voltage as a function of time, again we could be talking about current in either case, is still just the sum of these two exponential terms with the coefficients a1 and a2. Okay, so that one's basically what we saw before. But now for the underdamped case, we're dealing with complex roots, so that changes the form a little bit. So here the voltage would take the form, I'm going to change the coefficients just to indicate these are a little bit different. So we'd have b1 times exponential minus alpha t times cosine of omega d times t. I'm going to define what this omega d, that's a different frequency that we're going to include now. I'll define that in a minute. Plus second term, which is going to include a second coefficient b2 times the same exponential minus alpha t times the sine of omega dt. So this omega d is indicated or noted as the damping frequency and is defined as such. Omega d is equal to the square root of alpha squared minus, I apologize, not alpha squared, omega naught squared minus alpha squared, okay? So basically if we have already solved for what omega naught and alpha are, we could use that to solve for omega d, our damping frequency, and plug that into the form of the solution that we have in the underdamped case. And then finally, for the critically damped case, the form of the solution would be as follows. So the voltage is going to be a different coefficient here, just d1 times t with an exponential minus alpha t, plus d2 with the exponential minus alpha t, okay? So each of these three solutions are what we should basically end up with based on, and again, remember that omega naught and alpha are going to be based on your elements, your R, L, and C quantities. So if I make a change to maybe my resistance, that may change the type of damping response that I have, and therefore that's going to change which of these solutions that I need to be working with, okay? So that basically gets us to what we wanted to have in the end, but now the only kind of question left is, well, certainly we know how to find the roots, S1 and S2, we know how to find alpha, we know how to find omega d, but what we don't quite know or what we haven't discussed yet is what these coefficients A1 and A2, B1, B2, D1, and D2 are. So I'll kind of map out how we get to that, but the basic idea here is looking at initial conditions, okay? So if we think about maybe in the overdamped case, if I'm talking about the voltage at time t equals 0, well, that means I plug in 0 to time t here. Well, that means both of these exponentials go to 1, which means I'm left with the voltage at time t0 is equal to A1 plus A2. So then I would want to look at my circuit, okay, if I maybe have the parallel RLC circuit as such, and maybe the voltage, again, here indicated as across the capacitor C. Well, that initial voltage V of 0, if I have some initial voltage here, that is what I would use to set that equal to A1 plus A2. So that's the general idea. The second initial condition that we'll need, because we have two unknowns here, we need two equations, is to actually take the derivative of any one of these response equations. After taking the derivative, set time t equals 0, and again, solve for what you have left. That will get you a second equation to solve for your second unknown. And in that case, you'll just need to know what the change, the dV dt or di dt, depending on the case, is at time t equals 0 in your specific circuit, okay? So I'm going to clean this up, and again, we'll kind of evaluate specifically how to find those coefficients for each of these three different cases. Okay, so again, we're talking about now how am I going to go about finding the coefficients A1 and A2, or B1 and B2, or D1 and D2, depending on the type of response that I have. And again, I just said that for doing this, basically we're going to take that form of the solution that we just had, plug in t equals 0. We're left in the overdamped case that the voltage at time t equals 0 is simply A1 plus A2. So again, if we look at whatever the circuit that we had might be, evaluate what that voltage is at time t0, then we can plug that in here. The second one then is to say what is dV, the derivative of the voltage at time t equals 0. So again, taking that same equation, taking the derivative, plug in t equals 0. This ends up, in this case, just being equal to A1 times S1 plus A2 times S2. Okay. Now again, here for finding the derivative of the voltage as a function of time in my circuit, well, here I might want to look at, in this case, let's say the current through my inductor, let's say, could tell me something about the derivative of the voltage, again, just looking at the standard relationships for inductance. Or if we were doing the opposite, if we had to find di dt, we might look to the capacitor because we could evaluate what di dt might be in that case, okay? So now for the underdamped case, again, if we just plug in t equals 0 to the solution that we just had up on the board, Here we would just have, this would tell us immediately what our first coefficient b1 was, and then taking the derivative of that function, and again setting equal to 0, would leave me with minus alpha times b1 plus omega d times b2. Okay, so that would be the second equation that we would need to solve for both of those coefficients. And in the case of the critically damped response, what we'd have is the voltage at time 0, t equals 0 is going to tell us d2. And then looking at the derivative of the voltage at time t0 is going to be d1 minus alpha times d2. Okay. So again, it's still a process of, you need to know initially what the type of response that you have is. That tells you the form of the solution, and then these relationships are going to what you use to help you to evaluate what your coefficients are. That would then allow you to write the final solution. And if you're curious, I do have some other videos that look at specific problems with RLC circuits that will maybe tell you a little bit more specifically how we can go about finding these coefficients, but this is what we can use in general. Okay, so let me finally wrap up with just one other topic here, defining or looking at really briefly the difference in the step response versus the natural response here, where step response means when I'm asking the case of if I were to add in a voltage source, let's say in the series circuit, or maybe a current source in the parallel circuit, well, that's going to have an impact then on the forms of the solution, but actually we see that it all works out to be quite even, more or less. So I'll just make a couple of quick comments about that, and then we'll be done for this video. Okay, so now just a couple of quick comments about the alternative case that we could have. We're just talking about natural response. That's where we're looking at voltages and currents that are going to decay down to 0. The opposite case that we could be evaluating is a so-called step response case. This would be where we're actually charging up a capacitor or an inductor in an RLC configuration. Again, we could have a parallel combination or the series combination. And here I've just kind of evaluated, maybe I have different sources and there's going to be some switch. So let's say at time t equals 0, we're going to close that switch. That's going to start to charge up my inductor capacitor with this current source or with this voltage source here in the series circuit case. So again, we won't go through the whole process that we just did for the natural response case, but the idea is really still the exact same in that in thinking about the parallel circuit case, if we applied KCL at this top node, evaluate all the currents, it would still be the same. The only difference now is I have a current here. I'll just indicate this as being the current I, let's say. And what this would tell me then is if I do the same process and evaluate my KCL equation, do the same kind of manipulations, taking the derivative, dividing by the capacitance C, what I end up with is the second order differential equation that looks like this. We're doing d squared IL dt squared plus 1 over RC times first derivative. And here we were specifically kind of evaluating in terms of the current IL. So 1 over RC and then plus IL over LC equals I, the current I from the source, over LC. So you see here that the form of this equation is more or less the same. The only difference is that I'm no longer equal to 0 on this side because of the fact that I now have an actual current source in the mix. And I could do the same thing for my series circuit. Now here I would be applying more of a KVL approach, but kind of coming out to, again, a very similar form to what we had previously. The only difference is going to be that I have to add in this voltage V right here. So I got the second derivative term plus R over L dVC if we're evaluating with respect to the voltage on the capacitor, plus VC over LC. All of this equals V over L times C. Okay, so now there's a whole process again we could go through for evaluating the forms of the solution. Here it's a little bit more tricky in terms of this differential equation because it's no longer equal to 0. It's actually equal to a constant value over here. So the math involved is a little bit more involved, but the main idea, if we were to go through that whole process, we would actually see that for the step response, the form of any of the solutions, let's say for the first one, for the parallel circuit case here, that IL of t would be equal to whatever, let's say I final was. So here we were talking about the current through the inductor here. We would evaluate what should be the final value of the current through that inductor, and then add on to that the form of the natural response. Okay, and then similarly, if I were thinking about the series circuit case, so I would say VC of t is going to be equal to whatever V final was. Here I'm talking about the voltage across the capacitor, what's the final voltage there, and added onto that would be whatever the form of the natural response dictated, okay? Again, I'm not going through the full analysis how we get to that, but again, this is basically saying that you can take everything we just talked about and how you find the natural response, and I can do the same thing in these step response cases, and the only difference I have to do is add on to that the final value of each of these. Now, one other difference will be when you're doing the natural response, those initial conditions, might be a little bit different, and also you'll need to think about that when I'm taking, like let's say the current at time t equals 0, well, that's obviously going to be whatever IF happens to be plus then maybe your coefficients that you had over here. And then if I was taking the derivative of this, di dt, evaluating at time t equals 0, again, in this case, taking the derivative here, the final value would cancel out, so I wouldn't have to worry about that there. But you just needed to pay attention to that, again, when you're thinking about doing, finding those coefficients for these natural response cases, okay? So again, hope that just gives you a real broad idea of the general process we can follow for any kind of RLC specific to the parallel and series case. Again, if you want to see some examples, I have some other videos posted up that work through some actual problems here. But this is just to give you an idea of how we can approach any given general problem, all right? So I hope you enjoyed that, and I'll look forward to seeing you on the next video.